So hi, good afternoon to everybody, and welcome back to our seminars from the Group of Orbital Dynamics and Planetology. Today we have the pleasure to have Christina Schoettler. Christina got her physics degree from Open University in the UK, a master in astrophysics from Liverpool John Moores University, and a PhD from the University of Sheffield, also in the UK. Currently, she is a research associate from the Imperial College in London. So please, Christina, the podium is yours.
Thank you, everyone. I just noticed all of my research is very UK-based. So I could never do astronomy in a different language because all of my astronomy, even though I'm German, I could never do it in German. So, but anyway. So okay. You should see my presentation now in full screen, I hope.
Yes, it's fine.
I'm just gonna pop a laser pointer on here, so I feel like I have a laser pointer here. Anyway. Good. Thank you for the invitation to talk to you about my research, what I'm currently doing, a little bit of what I have been doing in the past, and all throughout my PhD and now my postdoc position. I'm interested, I have been interested in the effects of dynamical interactions on stars and planets in their birth environment. We see one of those birth environments here on the left, and we'll see a few more further down the line. But stars do not form in isolation. They actually do form with other stars together. So there will be some effect of these environments on the evolution of stars and also on the evolution of planetary systems that might have already formed around these stars. Let's quickly go or have a look on the outline or structure of the talk. I'm briefly going to talk to you about the effects of dynamical evolution in star-forming regions that we have found mainly from simulations to figure out, because of course what we see out there is a snapshot of the current state of star-forming regions, and we still don't know a lot. Well, we still don't know a lot, or not as much as we would like to, about how these regions might have formed, how they have gotten to the way they look right now. I will then go into some of my research that has taken me throughout my PhD, which is actually constraining star cluster formations, so figuring out how these star clusters could have formed using ejected stars. So the stars that are no longer part of a star-forming region that have been kicked out, often as a consequence of dynamical evolution, so dynamical interactions, n-body interactions in these kind of environments. And these dynamical interactions can also have an impact on planetary systems or also disks that are formed around this, the stars in these stellar clusters or stellar associations. But I'm focusing on planetary systems in my work. I haven't gotten to the effect on disks yet. So I've already briefly mentioned the birth environment that I've started my talk with. Where do stars and planets form? They form in grouped and clustered environments. We see a couple of examples here. These are very, this is a starburst cluster and some other clusters and stellar associations here, which can either be bound or unbound. But the main thing to take away from these birth environments is that the stellar density, so how many stars we have in a certain volume, is much higher at these early stages when a star is still within the star cluster, compared to the densities of stars that they will later experience once they have dispersed into the field, because often these star clusters and stellar associations don't last forever. Often they disperse after 10 million years. Often they can also just disappear after the first supernova explodes and kind of disrupts the whole star cluster. And then it can be no more after a first supernova or after 10 million years. Of course, we know also older clusters, open clusters that are several 100 million years old. So there are clusters that survive, but it's about only 10% that survive or are thought to survive past the 10 million year stage. Let's start looking a little bit into the effects of dynamical evolution on young star-forming regions. And I always like to headline it with what we observe now of these regions is likely not what they looked like when they were born. So if we're trying to figure out star formation theories, we might need to get a better idea of how these regions where we can only take a picture at the current point of the evolution might have looked like at an early stage. And I've done this all throughout my PhD, and I still use the information of the dynamical evolution of these young star-forming regions now in my postdoc work. And I'm working on this using n-body simulations. And this here is an n-body simulation, a typical n-body simulation that I use. And I gather information about the amount of dynamical interactions, how they evolve, how stars get kicked out. And this is a typical view of one of my star clusters. You can see that the stars here in two different colors. The darker colors are the smaller stars, so the lower mass stars. And the couple of red dots here that you can see under my laser pointer are the higher mass stars. These are stars over 8 solar masses, which follow a slightly different evolution because they eventually might explode in a supernova and therefore have a slightly different evolution. This is actually animated, so I hope it works. So we hopefully should see a little bit. So the stars are originally not homogeneously distributed, but in a kind of substructured way, which the idea of this is to represent, let's see if I can actually stop this, yes, to represent the filamentary nature of star formation. We have moved away from using more homogeneously distributed initial conditions where you use a plumbosphere, which is kind of density profiles that was derived from globular clusters. And with what I've been using, we're moving more towards something that is more representative of the filamentary structure. We have run this simulation, this n-body simulation, now only for 1.5 million years. We can see that up here. But we can see already now that the star cluster, even at this early age, looks very little like the substructured, clumpy star-forming regions that the simulation started with. You can see some of these stars have already gotten quite far from the star-forming regions, 2 or 3 parsecs. And also that the position of the high mass stars have actually changed compared to what they started with. Let's see if I can continue this. Yes. So we can see, I always call these like n-body simulations a little bit of an anthill because that's what they look like loads of little ants moving around. You can occasionally see stars here escaping the regions, which at this young age will be the result of a dynamical interaction. So 2 binaries or a binary and a single star interacting with each other, and they whiz around and exchange some of their components. And at some point, one of those stars gets kicked out from the cluster. We now get to the final point, the 4 million year stage, which is what the age of what this star cluster simulation has been run to. And we can see something that looks similar to some of the examples we have seen in the observational pictures just a couple of slides back, with a centrally concentrated clump of stars and a slightly broader distribution of often kicked out stars. So this is likely a runaway or an ejected star. These here that have already reached 75 to 100 parsec after only 4 million years have been kicked out rather rapidly. But what we see here is that this cluster looks very little like what has started the simulation. So just by taking a picture of a star-forming region at this current point in time, it's very difficult to derive the initial conditions, so the initial density, how the stars were distributed, what the kinematic initial setup was like, if it was already virialized, if it started its evolution subvirial. It's very difficult to derive this from a picture that you take after a couple of million years. Some of the things that actually disappear or gets erased during this kind of early dynamical evolution is this initial substructure. We see this on the top here. On the left, once again, this kind of clumpy initial distribution of stars with the triangles now in red showing the higher mass location. And after 5 million years, these n-body simulations show a similar picture like the moving pictures we have just seen in the previous slide. We can see that the initial spatial clumpiness has disappeared It looks more like a more centrally concentrated cluster, which then decreases in density as we move out. We can also see dynamical mass segregation, which means that in this point, the higher mass stars that were distributed across the star cluster initially have moved towards the center, which is also something that is shown here in the center. Initially, there was no mass segregation, which is represented by this kind of indicator. And we see after 5 million years, the first 7 to 8 highest mass stars are mass segregated. So the high mass stars during the dynamical evolution move towards the center and are then found in close proximity to each other compared to the low mass stars, which are then distributed across the region here. Another effect of the dynamical evolution of star-forming regions is seen in the reduction in density. So these regions start with incredibly high densities. We see here the density, the surface densities of stars in square parsecs. At the beginning of the simulation, we can see the blue is the density of the higher mass stars, and the red is the density or the area where the lower mass stars, and the red is where the density of where the higher mass stars are distributed. We can see we start with all of these stars around 10 to the 4 stars per square parsec, which is a fairly high initial stellar density, which is something that we think the Orion Nebula cluster has started as, with a very high dense region. And then during the early dynamical evolution, it has rapidly reduced in density. So the lower mass stars, after only 5 million years, have reduced in density by 2 magnitudes down here, whereas the higher mass stars are still more located in the higher density regions, which of course also fits with the mass segregation we have seen on the previous slide, where the high mass stars are located in the central regions of the cluster, which still show rather high stellar densities. Another thing that happens is destruction of primordial binaries. We know that most or many stars form in binaries. So also in the star-forming regions that I simulate, we have primordial binaries. Around 60 to 70% of the stars are in binaries. We can see this here, how these binaries with different initial conditions, this factor down here is a representation of how clumpy, so how many star-forming clumps you have. This is a very clumpy initial region here, and you get less and less clumpiness, and this is a very smooth, homogeneously distributed, spatially initial condition for the stars. But in all of these regions, we can see that the stars with different masses are set up with different initial primordial binary fractions. But all of these start with higher binary fractions that they end up with at the end. And of course, dynamical interaction and body interaction, so things interacting with each other, are quite capable at destroying the primordial binaries and then potentially also producing dynamical binaries that I might get the chance to talk about at the end. But we can see here that regardless of the initial spatial clumpiness or the initial spatial distribution of stars, that there's a destruction of primordial binaries. So if you look at a star cluster, maybe at 1 million years or at 10 million years, and then look at the binaries that you find in these kind of clusters, always keep in mind that these regions might have undergone quite a lot of dynamical evolution and might have started with a much higher binary fraction than what we observe now at the current state. Finally, I'm now coming generally to the effect of the star-forming environment on planets and protoplanetary disks, which are the formation locations of planets. And also dynamical evolution of these regions have an effect on the protoplanetary disks. We can see here work that has been done showing how quickly the percentage of disks can reduce in differently set up initial star-forming regions. This is a lower density star-forming region, only with 10 solar masses per cubic parsec compared to 100 solar mass per cubic parsec setup. And we can see here that when you start with every single star having a protoplanetary disk, that this protoplanetary disk can quickly get destroyed. And after 4-5 million years, we have about 20 to 30% of the total disks remaining. All the others have been reduced or destroyed by interactions with other stars. In more denser regions, this evolution is even more dramatic. You can see here how the percentage of total disks drops to almost zero after 2 to 3 billion years. And this kind of drop or destruction of disks can happen. We can see here the little graphical representation of two different kind of flybys, because dynamical interactions between stars is basically flybys of one star flying past another. We can see when you have a disk, this is the dashed line here, is the initial disk size. And if you have a more distant flyby here, we see this here, we can see that a flyby can actually induce or trigger spirals, which might then support planet formation because they change the density profiles of the disk. But they can also heavily disrupt the disk, so they can actually prevent or remove a lot of the material that might have been used for planet formation. And if you have a flyby that is much closer, a flyby that actually goes through the disk. In addition to disks being affected by flybys of stars in the star-forming region, we can also see, or there has been work done on the effect of a star-forming region evolving on a planetary system. This is a planetary system that has been set up with a single giant planet, which is currently still very difficult to simulate planetary systems in a big star cluster simulation. There are no codes which do it all the time, like immediately. So there's still quite a lot of little tinkering required to actually make it possible to evolve a planetary system of more than one planet in a star cluster. In this work here, the authors have used a single giant planet, which is basically set up as a binary partner instead of a higher mass solar mass binary partner. They set these simulations up with single giant planet as a binary partner. And we see here how after 10 million years, these architectures have dramatically changed. We see changes in semi-major axis, in eccentricity, and in inclination. The dark gray color here, we see it here. We can see here that these planets are originally set up at between 20 and 30 AU. And we see that preserved means that the giant planet is still around its original host. So it has not been become a free-floating planet, and it has not been directly stolen, because it's possible for a flyby to directly grab a planet from one planetary system and then it becoming a planet in another planet system. So in the preserved setup, we see that the semi-major axis with preserved planets after flybys in a star cluster do not rapidly change. However, when we look at the stolen planets, where one star flies by another planet system and just steals the planet, which is quite thieving, we can see that originally also these semi-major axes were the same as with the preserved, and they show some differences. The differences in eccentricity is much larger here. We can see this here compared to the preserved planets in gray, as the same as the inclination, which started with a zero inclination. So both of them at the same inclination. But we can see that especially inclination and eccentricity are a lot affected after evolution of a single giant planet system. Similar things happens with the captured planets. Captured planets are planets that were first released after a flyby from one planetary system, become free-floating planets, and then have been picked up by another star. So it's kind of a non-direct stealing, but more a capture process of something. But we can definitely see that there are differences in planetary systems that stay with their original host compared to planet systems that actually are around, not their original host, but another star in the star-forming system. This is just to give you a quick introduction about how important or how wide-ranging the effects of dynamical evolution of a star-forming region can be on the stars in the regions and also on planetary systems and disks itself. We're now trying to go back in time a little bit and look at some of my work that I've done, trying to figure out how could these star clusters have formed? What might they have looked like at the beginning of their evolution, after they come out of their gaseous phase, have started forming stars and started evolving under gravity. We can start here with two different theories of star cluster formation that we're still trying to figure out which of these might be the predominant factor. On the left here, we see the more classical view, which is a top-down in situ formation, where you have a big, giant molecular cloud, which collapses all in one go under its own gravity and starts forming stars at the center. These kind of star clusters, or this kind of formation scenario, is typical of starburst clusters, where star cluster suddenly emerges out of in a region where there previously was not anything. This is the originally or more classical view of how star clusters have actually formed. In this original view, there is a very clear formation or evolution process where a star or a big cloud collapses, forms a star cluster, and this star cluster then goes through dynamical evolution and eventually disperses into the field, becoming unbound and forming stellar association as a result. So this kind of evolutionary sequence is very prescriptive with regards to how things might have evolved. And we have found in observations that there seem to be some star-forming regions out there, so regions where stars seem to move in the same direction, might be bound, might be unbound, that do not kind of conform with this idea of having gone through a very dense star cluster phase before arriving at the phase that we're currently observing, which is where this second formation idea has then started to come up. Is known with many different ideas, which is bottom-up hierarchical collapse or hierarchical assembly formation scenario. We still start with a giant molecular cloud of gas, but instead of this cloud of gas collapsing in one go, it starts to fragment. It fragments into sub-regions, and then it can fragment even into much smaller further regions. And in these subclusters, you see then a collapse and a formation of subclusters of smaller regions of stars that form within this fragment of gas. And eventually, if these fragments or these subclusters are in close enough proximity to each other, they can actually start forming a star cluster at the end. This second scenario leaves a lot more open with regards to explaining all the different kind of star clusters or star-forming regions, stellar association we see out there. But just by looking at a star cluster now in observation, it's very difficult to figure out if it formed via the formation scenario on the right or the formation scenario on the left. There has been quite a lot of work in the past going on with trying to figure out methods of deducing of how did a certain star cluster form. Has it gone through a dense cluster phase? So is it kind of confirming the theory on the left? Or does it more look like something that has formed from a clumpy star cluster or clumpy subcluster evolution? During my work, I've actually tried to figure out or look if stars that get ejected by the dynamical evolution, which we have seen earlier already in the N-body simulation, and we now have here on the right a little cartoonish animation of one specific dynamical interactions between two binaries. And my work has looked at if this kind of result of dynamical evolution, which is unavoidable in this kind of dynamical evolution scenario, if these stars that get ejected from a star cluster, which are called runaway stars because they literally run away from their birth environment, could be used to actually tell anything about the underlying star cluster. So is there any difference in the amount, the number, the velocity of runaway stars for regions that were started with different initial densities, with different initial kind of spatial clumpiness, or how many fragments, how many clumps you have. And Early on, when I started this work, I basically set up simulation to just check and look, is there any difference in the fractions of ejected stars, depending on the kind of initial conditions that I threw in for the n-body simulations. All of these plots you see here are based on a clumpy initial condition spatially. So you have this kind of clumps of stars that are set up in the n-body simulation. And these are then set up with different kinematic ratios, which is the relation between the kinetic energy in the cluster compared to its total gravitational potential energy. I have two virial ratios here on the left, 0.1 and 0.3. Both of these are subvirial ratios, so the kinetic energy is completely overcompensated by the gravitational potential energy. And what happens in these kind of initial conditions is that the cluster collapses, goes through a cool collapse phase. It collapses dramatically and forms a very dense star cluster before it starts evolving into a virial equilibrium. The simulations here on the right are set up with being initially in virial equilibrium, so they're already balanced, have a balance between their kinetic energy and their gravitational potential energy. But all of these simulations have kinematically very different, evolving very differently, have been set up with this clumpy initial spatial distribution. So you have clumps of stars all throughout the region where you set up your star-forming region. And these clumps, the overall virial ratio is what we see here on the top. But in the clumps that you get, you can actually have subvirial, so cool initial conditions, which will then collapse the subcluster first. We can see here two different curves, which are the fractions of ejected stars over 10 million years simulation time. We have the bigger, brighter stars on the bottom in yellow, and the smaller and fainter stars on the top in red. These are the stars above 8 solar masses, and the other ones are the ones below 8 solar masses. And the main takeaway from this slide is that there seems to be a difference between the initial conditions just in this very, very basic setup, in that the fraction of lower mass ejected stars seem to be increasing the more virialized the region originally starts at. You can see then on the opposite side, the number or fraction of higher mass stars that get ejected actually decreases with the amount of virialized initial kinematic substructure. So this gave already us some ideas that there might be a difference in how many ejected stars, how quickly they are, what kind of masses they have around a young star-forming region. And this might be able to tell us something about what this region might have looked like initially. I took this initial result to the test and tested it on two different star-forming regions just to see if I look for runaway stars in observations with Gaia. Could I match the runaway stars that I found around different star-forming regions to simulations to deduce or get a good idea of what kind of initial condition and initial setup these star-forming regions might have had. And I'm showing you the results here for one of my star-forming regions, which is NGC 2664. It's still a very young region. It's a distributed region over quite a patch of sky with a northern and a southern subcluster, which are thought to be slightly differently aged. And the work or the results here are from the northern region, which is thought to have been slightly older. This is Gaia data here on the left and both on the right. And this is an HR diagram with the magnitude or G magnitude on the left and the color on the bottom. And the line here is a 5 million year parsec isochrone. What I did in Gaia is basically took a big patch, 100 parsec of stars around the central region, which is centered around a star, which is a very big star called S1. Took all of the data and looked at where the directions of motion of all these stars in this region of sky is using Gaia, proper motions, and radial velocities, and all the information about their positions. So basically, this is the picture here on the right, where it's a big volume of space with loads of stars moving in loads of different directions. And I identified several runaway stars that have a certain velocity in relation to their star clusters. Runaway stars normally have velocities over 30 kilometers a second in relation to where they come from. And walkaway stars are a bit slower, so this is why they're very fittingly named walkaways, because they walk away, not run away from their star cluster, are normally thought to at least be 5 kilometers a second, sometimes more, depending on the escape velocity of the star cluster. But we can see very clearly here how these stars, this is their vector of motion, how they move away from the center of this plot where the star cluster is located. There are lots more stars that you can actually trace back to this region here at the center. But if we then plot them on an HR diagram to see what might their age be, because at these very young star-forming regions, stars that have originated in this cluster have to be above the isochrone, or potentially with the error bars above the isochrone. We can see here on the main sequence of the data, we can see a couple of more stars that were possible to be traced back, but were too old to have originated from this cluster. So they might have been just coincidentally moving through this region at a time further in the past and just now point back to this star-forming cluster, but have never come from here. The numbers here, we have 1, 2, 3, 4, we have 5 runaways and a couple more walkaway stars. I then compared to several simulations that I ran with similar initial condition or possible initial conditions. I had from members list a good idea of how many stars there are currently in the cluster, and then ran a couple of possible initial conditions, starting with like very clumpy, very cool subvirial initial conditions, going all the way to smoothly distributed virialized initial conditions. And here, this is the maximum number of runaways I would have in a single simulation, so in a representative simulation after different times. The number of runaways decrease here after times because I set a boundary. So the runaway gets ejected, moves through the volume of space, and eventually passes the boundary, which is why these runaways decrease over time, because they have moved past my boundary, the 100 parsec boundary that I use in the Gaia data. We can see here, this is the runaways, the 5 runaways that we've just seen on the other slide. And for the runaways still present in close proximity of the cluster at 5 million, 4 million, and 3 million years of the simulation, the runaways in the simulation, or the maximum runaways in the simulation for any of my initial conditions, was actually much lower than what I found in the observations, which is up here. We have to go all the way to 1 and 2 million years of simulation time to find several of, or a couple of the initial conditions that have actually, or would predict more runaways or a similar number of runaways coming from these kind of initial conditions. And we can see up here 2 of these, which is the blue and the green one, which are set up with clumpy initial conditions that were either virialized, which is the 0.5, which is the green one, or subvirial, which is the blue one here. So they would go through a deep collapse phase and during this bit kick out these star clusters. So based on combining simulations and Gaia observations, I was able to constrain initial conditions, which is initial density, because my simulations were consistent with a certain initial density, and also say that they are very likely to have come from something clumpy. So clumps of star-forming gas and stars, either virialized or subvirial. In addition, or in a follow-up work that I don't have a slide for, but I just want to mention, we actually used a method that has been around for much longer than my ejected star method, and we found similar initial conditions, confirming that the runaway star initial conditions seem to be a usable method to constrain initial conditions, because you overcome the limitations of having to look in a very dense star cluster where it's difficult to find out a lot of information about the stars, because you have the issues of stars not being properly isolated or resolved in these kind of things, because ejected stars you normally don't find in the very clumpy busy areas. But let's move away a little bit from the stars and move to planets, because of course planetary systems, well, we know stars form in grouped and clustered environments, and planets form virtually or start forming virtually at the same time as the stars form. So it's likely that planetary systems might still be in these young star forming regions while they still interact with each other, where stars go flying past another star. And these dynamical interactions might have different effects on stellar or planetary systems in these around these stars. So what do we know about planet systems? We know quite a lot. I think in the past 10, 15 years, planets or planet searches and the finding of planets has massively taken off. And we now know over 5,000 planets in many different single and multi-planetary systems around a whole host of different stars. And this is kind of represented here on this mass orbital period diagram, where we see the different colors representing the different discovery methods for planet systems. One of the most productive methods to find planets is actually a transit method, which I'm going to quickly explain on the next slide. But we can see here we have a large number of higher mass stars, which are in the Jupiter mass region, and then we go to the lower mass stars. Earth is just put in here for reference, highlighting that the whole region where Earth and some of our other solar system planets are is actually still a fairly empty space in the plot showing what kind of stars we can actually discover. So the transit method is one of the methods that is very productive or effective at discovering planets, certain types of planets, often close-in planets, because of course in a transit method, a planet has to go in front of a star. So this is more likely or more supportive of stars that are close to the host between 10 to 100 days orbital period. So these are planets that are interior to our orbital location of Earth. Then we have here in green, these are radial velocity planets. This is where you kind of detect the wobble that is induced because when a planet moves around another star, or moves around the star and the planet actually move around their common center of motion. So the radial velocity method kind of detects a wobble in the star, in the motion of the star, and therefore is able to predict the presence of a planet that has to be there in order for the star to do this kind of motion in radial velocity. Based on all of our detection techniques, we have been able to detect quite a lot of different kind of planets. We have rocky planets down here, which are super Earth or Earth-like. Then we have the more giant Neptune-like planets. Then we have hot Jupiters here, which are Jupiter-like or Jupiter mass planets, but they're so close to their host star that they are very different than our own Jupiter, which is a cold gas giant, which sits further out here. And on here you see kind of just a quick representation of all these kind of different planets or planetary types that we have identified so far here. What does all of this has to do with the star forming environment or the star forming regions? I'm going to quickly go back into transit technology, transit photometry, the way of detecting planets or multiple planets when they move in front of a star, because we get a dip in brightness. And if we get dips of different length and of different depth, we can deduce that a star might actually have more than one planet. And the Kepler mission has been quite productive at detecting not only single transiting system where you only have one planet going in front of a star, but also multi-transiting system where you have more than one planet that passes in front of the star, creating different transit light curves that we see here on the right. And something that has then evolved or has been found out from these Kepler data. Kepler, I think, launched in 2009 and has been producing or has looked at a patch of sky for 4 years, trying to find as many planets around stars in this patch of sky as possible. And we see here, this is earlier this year, a histogram of all the planets, of the number of planets they have detected. Number of planets in this histogram is related to how many different transits have been observed. We can see there's a large number of single transiting systems. This could either be single planet or only one of those planets sits in the right plane of the sky so we can see it edge on. Then we have a smaller number of double transits, triple, quadruple, and kind of the number then starts to disappear. One of the interesting things that Kepler has found, or that we have found during this mission, was a planet type that we don't actually have in our solar system, which is a super Earth. Planets that are larger than Earth, much closer to the host planet, which is the kind of setup that you need to actually find transiting planets. Something big enough to block enough light from the host star, close enough that we can actually observe it properly. Because, of course, if you have to wait a year, 2 or 3 years to observe more than one transit, it might be quite difficult to confirm the planet. Anyway, looking at all of this observational data showing single transiting systems and then the multi-transiting systems, there was some work then undertaking following this work to figure out, are all of these planets, can they all have formed from the kind of same planetary formation ideas that we have known at the time? And we can see this here already, that the models, Lissauer et al. At the time in 2011 used Kepler data, trying to predict if the multi-transiting and single transiting systems could all be due to the same underlying planetary architecture. And they looked at many different models, and their models which matched these multi-transiting systems the best actually predicted much, much, much fewer single transiting systems. We can see this here. This is where this population model would have predicted what we observe in regards to multiplicity. But the Kepler data here, that was 2011, so you can see how many more planets we have found since then. But we can see that there's quite a large axis of single transiting systems that cannot be explained with the same model or planet formation model that forms the multi-transiting systems. I'm just looking at my time and I need to move on a little bit. So there are many different ideas trying to figure out why we either have only one planet in this planetary system to observe, or why we only see one planet. If there's only one planet there, there's no more planets to observe. But if you have more than one planet here, in order to observe them, they have to be very in the virtually coplanar alignment in order for all of them to transit. So the mutual inclinations, the inclinations between these planets, could not be too much in order for them to kind of disappear either to the top or to the bottom of the star. What in the current project we looked at is trying to figure out, could a flyby, so an interaction in a star-forming region, be responsible for causing misalignment of the planet? So the misalignment of the inclinations, so mutual inclinations that were too big to be observable together. And this then derives back to star cluster simulations again, and to the fact that about 40% of stars in these star cluster simulations have at least one close encounter. Close encounter, we can see here, this is the encounter distance, and this is simulation time over 4 million years. And we can see here that the encounters get bigger at the early stage, which is where the cluster collapse, where it gets denser, where stars are much closer to each other. So they have a much higher chance of actually interacting with each other. But then shortly thereafter, the interactions actually start to level off and become as almost a flat line that just continues evolving over time. You can see here, when we look at the histogram of the encounters, we can see that encounters further away from the stars are actually seem to be not quite as common as the close encounters, which seem to be here much more predominant in these kind of star cluster simulations. This is a single simulation here on the left. I run 20 of these simulations for every kind of initial combination of densities and substructures and other stuff. And on the right, we see 20 simulations put together. We can still see the same kind of picture that we see on the histogram here, that there is a lot of close encounters. The percentage of closer encounters seems to increase and then kind of drop off and then level off to like 1 to 2, 1.5% for each of these bins of 20 AUs. And actually half of all encounters in my simulations are below 300 AU. Now, the idea was take a flyby, have a single flyby, not any kind of multiple flybys, and see what happens to a planetary system that would be typical of those that we can observe with Kepler or could observe with Kepler. I ran about 600 simulations of many different flybys. We have general architectures around this one solar mass host. We see this here on the right. The host in the center, then 4 planets, which are 5 solar masses, all coplanar, all circular, so very, very simple setup. These simulations without a flyby are stable to 500 million years. So they don't collide, they don't become largely mutually inclined. So in isolation, without a flyby, we would still observe these as they were when they formed. The inner planets are very close, between 0.1 and 0.2, which are typical distances for Kepler planets. In addition, we also put a giant planet of 5 Jupiter mass planets at 5, 10, and 20 AU further out to see if the disruption or disturbance of the giant planet could actually filter inwards and affect the inner system afterwards. Here, this is a 50 AU flyby by a 0.5 solar mass star. I tested 3 different masses. They flew by at 2 different velocities. They came from 2 different directions and at 3 different flyby distances, 50, 150, and 250. The flyby was within the first 20,000 years, so virtually at the beginning of the simulation, and we then ran the simulations for another 500 million years. One of the first things to note is that planets get lost via collisions with each other fairly quickly. We can see here, this is the average number of inner planets at the different flyby distances, and we can see all start with 4. The 50 AU curve starts to drop off very quickly when the number of planets starts reducing. So they go from 4 to 3 to 2. And here on the right, the histogram shows the number of planets after 500 million years due to collisions only. These are, they are due to collisions. And so we have 2 planets left in a lot of these simulations. So if these 2 planets are not at the right inclination after colliding with other planets, you would only be able to see one of them. The most we could see from this planetary system is 2 planets or 3 planets, because of all the 4 planets have virtually disappeared. So one of the ways of explaining or trying to explain the Kepler dichotomy, so the excess of single transiting system, is actually losing planets due to collisions with each other. The second explanation is actually the mutual inclination. They start all coplanar in the same patch of sky and start increasing. What we see here is once again the 3 distances, and we can see mutual inclinations above 4 degrees. So they have to be quite a way away from each other for us to be above a boundary. But for 55 million years, nothing actually happens. They are fairly stable for quite a while. And then all of a sudden, the first simulations start showing these mutual inclinations. So the planets interacting with each other and starting to drifting apart from each other. And we can see this here over 500 million years, that the closest interaction or disturbance flyby creates the most simulations with actually excited inclinations of the planets. We can see this here as well. This is simulated transits. We can see at 0 million years, the distribution changes rapidly towards from 4 planet systems transiting to virtually single transits for quite a large number of stars. We still have a couple of two planets transiting, but you can see that the evolution over time towards the single transiting systems here. So this could potentially be a way to explain that reducing due to collisions and then the shifting of the mutual inclinations to actually explain the Kepler dichotomy. When we now finally look at the Kepler data compared to our simulated transit numbers, the Kepler data here is in blue in the back, and the same kind of 500 million years histogram we've seen in the previous slide is plotted here in the green overlay. The data is scaled in such a way that the two transit system matches between my simulated data and the Kepler data. And while we see a motion of the four planet systems, or four transiting planet systems to single transiting systems, after 500 million years, there's still not enough single transiting system to explain all of these single transiting systems we observe. But we see that over time, the number of planets transiting reduces in the simulations. I can stop here, or I can move slightly to one last project that is still in the very early stages, but I think given that we have, it's 10 to 7 my time, I could finish here and just skip over the last bit, and we could talk about this if anyone's interested. Anyway, takeaways. Star-forming regions evolved dynamically very quickly over just a few million years. So whatever we see now, keep in mind, there might not be the stage how these regions looked like just a few million years ago. So they can evolve really quickly. Dynamically ejected stars can be used to better constrain initial conditions, to put a lid on what they might have looked like in the past, allowing us to better figure out how they formed, star formation theory, star cluster formation. And that young planetary systems can be significantly affected even by just a single close encounter. But one of the things I've learned, it takes a while. So patience is one of those things that is really, really important when you have flybys or try to see what happens to a planetary system. And this brings me to the end. Thank you. And do we have any questions?
Thank you, Christina. Fantastic talk. I think very interesting. So we are open for questions or comments. Anybody would like to make a question or a comment?
I quickly end my slideshow so I can actually see the group. Thank you. Thank you for listening.
Okay. Well, I have one other question in terms of in your, as a dynamicist, we always care about the details. So in your first slide where you showed the animation, how do you distribute the initial velocities in the clamps? You consider as a stable situation near circular orbs? Well,
I'm just going to quickly go back. So these simulations, I'm just going to see if I can actually, I'm trying to move around my PowerPoint without being in my PowerPoint. I'm quickly just going back. So these simulations are set up using something called a box fractal, so the fractal method, which has been developed by one of my second supervisor. And it's kind of the velocity structure. They inherit velocities, so you kind of shift velocities down from parent to child. So the moment you add a star, it inherits the velocity from its parents. I think they initially set up fairly random, but how it comes out as is that stars that are close to each other have very similar velocities, whereas stars that are further away from each other can have very different velocities. And it's all done in the black box because I'm not really working with this bit anymore. So I can have a look at it, and I can maybe send you something if you're interested, just to see how this is set up. But it's quite a cool bit.
Okay, yeah, I'd like to know, because we have some other completely different scenarios, other studies, and that's something very sensible in our case. So if we give you some, let's say, some eccentric velocity, it completely changed the scenario afterwards.
Yeah, no, it's just like I see this like with the different virial ratios. The moment you change like how the overall virial ratio is, that changes a lot of the picture as well.
Yeah, I know. So anybody want to make a question, interrupt me. I have another one here by myself. These interactions, when you talked about the disk and the interaction of the stars with disks, and did you analyze, or did anybody analyze or discuss the change of elements, volatile elements, going from the outward parts of the disk, mixing that? Because there is, you know, that in the solar system there is a huge discussion about volatiles getting inside the terrestrial region, and there are a lot of things always involving just the planets, or the migrations and that. But my question is, if you may have already a planet and you still have the disk of gas and you have an encounter, so what would that make in terms of moving material outside to the inner region?
That's a good question, and I'm not entirely sure if anyone has. I have been interested in disks, but I'm an n-body simulator, and I haven't actually looked into hydro simulations yet. So, and I'm not working a lot with disks, but I could have a look and see, because I have a couple of colleagues who might have a better idea if there's anything. So I'm just going to put this down as well as something to look at later. Disks distribution. Because that might be something, because of course these flyby, like especially fly-throughs, because of course if you have a disk like several hundred AUs like in diameter or in radius, and then you have a flyby at 100 AU, and something must disturb it. Sure. It's probably a bit easier to.
Yeah. I think that would be something really, really interesting, a different way to discuss the mixing of materials.
Yeah, I think that's true.
And the final one is just a comment in your first part, where you discuss how could you see the planets during the transit. If you have a slightly large inclination, you would not see it. So my point is, we have 8 planets in the solar system. All of them would be seen.
I think the inner. Yeah, more exactly. Well, the mutual inclinations between the solar system planets, I think, are not quite so big. So, well, further out you go, you will lose planets, because, of course, you need to have exactly the right angle between viewing and all of this. But I always wonder what aliens will see of our solar system if they were observing us.
Yeah, but anyway, would we be a kind of exception? We didn't have much close encounters or things like that. Can you say something in that sense?
Well, having 8 planets to start with is already a hint that maybe, because of course, especially because they're quite distributed along. So based on what I have looked at, it's likely that the solar system comes from either a lower density region in a cluster or hasn't had loads of encounters. Because of course you still have fairly coplanar, fairly circular orbits. But there has been some work done to try to explain Planet 9 as the result of an encounter. Well, we don't know if Planet 9 is around, but there has been some work done. It was while I was a PhD in Sheffield. A colleague of mine, she looked in trying to figure out if like a weird inclination, because anything that has a weird inclination, a weird eccentricity, because like if you have a planet orbiting like this and another like this, it's very difficult to get this to form in the same disk. So there has to be something. But as the solar system is like fairly flat, I personally think, and has still quite a bit of planets and everything, but I think there has been some work done recently on the trans-Neptunian objects, that they might have been disturbed in a way due to a flyby. Because I was at a conference recently in Porto, where like the poster next to me talked about encounters being responsible for like the way the trans-Neptunian objects are distributed. So that was quite an interesting bit, but yeah. It's kind of always trying to figure out like where have we formed and how are things. Bye, Antonio.
Okay, good. And just another curiosity, what about the spin axis, the obliquity of the stars? How would they change during these encounters?
That's something that I'm not looking at. So in my planet simulations, I haven't gone all the way to have a look what actually happens to the inclination of the central star in relation, but the planetary system. So some of my planetary systems during a flyby, they actually get dragged towards the flyby, and then they kind of change. So there is definitely a spin orbit axis alignment difference after a flyby of many of the stars. But yeah, this is still analysis work, because my simulations, I'm still waiting for 5 to finish to 500 million years. So because of course n-body simulations, the longer they take, the more happens, which is always quite curious, because you wait the longest for those which are really interesting.
Yeah. How long do you take in your simulation? The real time?
Real time is normally 30 to 40 days per simulation, and longer when really interesting stuff happens. With n-body, it's so unpredictable. So you can't say, oh, my simulation is finished next week. Some of them, I want to run them longer, but n-body is always an issue, because of course they can run really long. But it's one of the things here I've learned, that a single flyby, or flybys in general, itself, the flyby might not disrupt the system by much, but like it excites the system, and then kind of it takes a long time of like very small, like just secular changes before anything happens. So the first 100 million years, I had barely any disrupted or any kind of systems that were not still coplanar and didn't show anything weird. So it was a bit of waiting to be done with this one.
Okay, good. So I think that's it. We'd like to thank you again. It was a great talk. I think very interesting. A lot of subjects to think, and perhaps to plan some other research.
Exactly. Just send me an email if you have a question, or if there's anything that didn't make any sense when I was talking about it. So please let me know.
Okay. Thank you.